For decades, humanity imagined the edge of the solar system as an invisible frontier, a place where the sun's influence gradually disappeared and the unknown began. Then Voyager 2 went there. Launched in 1977, Voyager 2 was built with technology that now seems incredibly primitive. Its computing power was tiny compared with modern devices, yet the spacecraft has survived for decades, traveling farther from Earth than almost any other human-made machine. Its journey eventually carried it toward the outer boundary of the heliosphere, the enormous region of space dominated by the solar wind. The solar wind is a continuous stream of charged particles flowing outward from the Sun. As it travels through space, it creates a vast protective bubble around the solar system. But that bubble cannot extend forever. Eventually, the outward pressure of the solar wind encounters the surrounding interstellar medium. At this frontier lies the heliopause, a boundary separating the solar environment from interstellar space. For scientists, Voyager 2 offered something extraordinary. A spacecraft was actually crossing that boundary and sending measurements back to Earth. In 2018, Voyager 2 crossed the heliopause and entered interstellar space. Its instruments detected a significant change in the surrounding plasma environment, providing direct evidence that conditions outside the heliosphere were different from those inside it. The discovery changed the way scientists think about the edge of our solar system. The heliosphere is not simply an imaginary line drawn around the planets. It is a dynamic structure shaped by the Sun, the solar wind, magnetic fields, and the surrounding interstellar environment. And the boundary itself is not perfectly fixed. The Sun goes through an approximately 11-year cycle of activity. During periods of stronger solar activity, changes in the solar wind can alter the size and shape of the heliosphere. During quieter periods, the balance changes again. Voyager 2 therefore isn't simply traveling through empty darkness. It is measuring a constantly changing environment. Beyond the heliopause, the spacecraft detected differences in plasma density and energetic particles. These observations helped scientists understand how particles behave when the solar wind meets interstellar space. Another fascinating feature involves magnetic fields. The magnetic field carried by the solar wind interacts with the magnetic field of interstellar space. Understanding how these fields meet is essential for understanding the heliosphere itself. Voyager 2's observations showed that this interaction is more organized than scientists once imagined. But there is an even bigger reason these measurements matter. The heliosphere acts as a partial shield against high-energy cosmic radiation originating outside the solar system. By studying what happens at its boundary, scientists can better understand how our solar system interacts with the wider galaxy. And that could eventually help us understand environments around other stars. Every star with a stellar wind may create some kind of protective region around itself. The size, strength, and structure of that region could influence the environment surrounding its planets. So Voyager 2 isn't merely telling us where the solar system ends. It is helping reveal how stars carve out enormous bubbles in the space around them. And the deeper Voyager travels, the more important its measurements become. Because beyond the heliosphere lies a region humanity has never directly explored with a spacecraft designed specifically for interstellar science. Voyager 2 is giving us our first real glimpse. And what it finds there could change how we understand the boundary between our solar neighborhood and the rest of the galaxy. But crossing the heliopause was only the beginning. The real mystery is what Voyager 2 discovered after entering interstellar space. Once Voyager 2 crossed the heliopause, it entered an environment unlike anything it had previously experienced. For the first time, its instruments were measuring the interstellar medium directly. And the results showed that interstellar space is far from the completely empty void people often imagine. There is plasma. There are magnetic fields. There are energetic particles. And there are constantly changing interactions taking place across enormous distances. Voyager 2's measurements revealed that the density of plasma outside the heliosphere was substantially different from what the spacecraft had experienced inside it. That difference was important because plasma density helps scientists understand the physical conditions of interstellar space. The spacecraft also detected changes in energetic particles and cosmic rays. These particles can originate from powerful events throughout the galaxy, including stellar explosions and other energetic processes. The heliosphere blocks or redirects a portion of this radiation, meaning Voyager's journey beyond the heliopause gives scientists a rare opportunity to compare the environment inside and outside the solar bubble. But perhaps one of the most fascinating questions concerns magnetic fields. The solar system is moving through the Milky Way, and the surrounding interstellar space has its own magnetic environment. At the heliopause, these two systems interact. Voyager 2's measurements helped scientists investigate how the Sun's magnetic influence connects with the much larger magnetic environment of the galaxy. This isn't just an academic question. Magnetic fields can influence the movement of charged particles across space. They can also affect how cosmic radiation travels through different regions of the galaxy. Understanding these interactions could eventually help scientists understand the environments surrounding other stars. And Voyager 2 has another remarkable advantage. It has been operating for nearly 5 decades. Every year that it continues working gives scientists another opportunity to study how the interstellar environment changes over time. But the spacecraft itself is slowly running out of power. Its electricity comes from radioisotope thermoelectric generators, which have been producing energy since launch. As the radioactive material naturally decays, the available power gradually decreases. Engineers therefore have to make difficult decisions. Some instruments and systems must eventually be switched off so that the most important scientific equipment can continue operating for as long as possible. This makes every remaining transmission increasingly valuable. Voyager 2 also carries something much more symbolic than its scientific instruments, the famous Golden Record. Attached to the spacecraft is a collection of sounds, images, music, and greetings representing Earth and humanity. It was never designed as a practical communication system. Instead, it was a message placed aboard a spacecraft traveling into the unknown. Today, its meaning is even more powerful. Voyager 2 has crossed the boundary of the Sun's immediate influence and is continuing into the wider interstellar environment. It represents something extraordinary about human exploration. A machine designed nearly 50 years ago is still sending information home from a place no human has ever visited. And although Voyager 2 will eventually become silent, its journey will continue. The spacecraft will keep drifting through interstellar space long after its instruments stop transmitting. Its mission demonstrates that exploration doesn't always require a spacecraft to arrive somewhere and immediately return. Sometimes, the greatest discoveries come from simply going farther than anyone has gone before. Voyager 2 has shown us that the edge of the solar system isn't a simple wall. It is a complex, dynamic frontier where the influence of our star meets the environment of the galaxy. And for the first time, humanity has a machine crossing that frontier and telling us what it finds. The journey isn't over yet. And somewhere in the darkness between the stars, Voyager 2 continues moving forward.